The eye is an amazing, complex part of our body with many functions. Some of its functions include a sense of direction, movement, color, detection, and distance. Today we will be focusing specifically on image formation and some common issues that may arise within our own eyes. Geometric optics allow us to analyze image formation by our eyes and understand common vision corrections. Before looking at the eye, it is crucial to understand a few things about light rays and how they work in nature. Light rays travel in straight lines called rays. These lines change direction when encountering a different medium, such as glass or water, but then the rays continue in a straight line. The two specific laws that determine how the light changes direction are the law of reflection and the law of refraction. Reflection is when the light rays come in straight but then bounce off matter. Reflection is very common and is seen when looking down into a pond and an image of yourself is projected back at you. Reflection occurs on both smooth surfaces, such as a mirror, and rough surfaces, such as paper. The difference is that a rough surface will reflect the incoming rays into many different directions, rather than just one direction, as seen with smooth surfaces. Refraction is when the light rays come in straight and pass through matter, rather than bouncing off, changing directions in the process. Refraction is also very common and is seen when looking into a fish tank and seeing multiple fish when in reality there is only one. This optical illusion is due to the light changing directions when it leaves the tank. The reason why the light changes direction when encountering different materials is because it changes speed when going from one material to the next. This is clearly seen when a car is driving on pavement and hits a patch of mud at an angle. The first tire that hits the mud will begin to immediately slow down, while the tires still on pavement continue at the original speed. Due to one tire going slower than the other, the car will begin to turn, changing directions and now moving at an angle. This is also shown when the lawnmower goes from the pavement to the grass, becoming slower as it encounters the grass and turning at an angle as well. An easy way to measure the stickiness or resistance of a certain material is by knowing the index of refraction for that given material. When the light rays enter a material with a low index of refraction, the angle of the light will be very close to the normal direction the light was originally traveling. Whereas if the index of refraction is big, the light ray will bend tremendously compared to the original path taken. In this picture, diamond has the greatest index of refraction, so it bends the most. One way to understand reflection, and especially refraction, on a deeper level is by looking at lenses. Let's examine a convex lens. Light rays enter the lens perpendicular to the surface, but upon entering the lens, the top and bottom rays will bend, down or up respectively, whereas the middle ray will continue straight. These rays will then cross each other at a single point on the opposite side of the lens. Where the rays cross is considered the focal point, and the distance from the center of the lens to the focal point is considered the focal length. These rays will change direction both upon entering and upon exiting the lens due to the change in material. All convex lenses will produce real images rather than virtual images. Concave lenses differ in the fact that instead of the rays bending towards each other after exiting the lens, the rays will bend away from each other after leaving the lens, and the focal length will be in front of the lens, not behind it. Lenses are all around us, in microscopes, cameras, telescopes, but today we will be focusing on the lenses within the human eye and how refraction applies to them directly. The anterior portion of the eye is composed of the cornea and lens, which can be treated as a thin single lens, even though the light rays pass through different layers of material, such as the cornea, aqueous humor, and several layers in the lens, changing directions of the rays at each different layer. A thin lens is one whose thickness allows light rays to refract, but is thin enough to only bend the rays once. The image formed from both the lens and cornea is similar to the image produced by a single convex lens, producing rays that converge on the opposite side of the lens at a circle focal point. As light rays enter the eye, the lens will adjust by varying the power and focal length in order to produce a real image focused on the retina, or the back of the eye, for objects at different distances, the lens becoming either thick or thin as shown in the slide. Due to the lens being composed of multiple layers, the lens contains varying indices of refraction. These refractive indices are crucial to image formation and focusing images onto the retina and will cause the rays to bend depending on the given material. Though the lens contains varying indices of refraction, the biggest change causing the bending of rays occurs at the cornea, placed anteriorly to the lens. Light rays that enter the eye will bend according to these differing refractive indices. For clear vision, a real image must be focused directly onto the retina, which lies posterior to the lens. The image must fall precisely on the retina to produce clear vision. The eye manages this by changing the power and focal length of the lens to focus on objects at various distances. Accommodation is a term used for the process of adjusting the eye's focal length. A person with normal or ideal vision can see objects clearly at distances ranging from only a few centimeters to practically infinity. Though the image must be projected onto the retina, the center of the image will fall on the fovea, a portion of the retina, where the greatest density of light receptors lie and where the greatest sharpness of the visual field is found. This image and the light intensity of the image must be controlled in order to prevent damage to the eye. The pupil, or the black hole of the eye, along with chemical changes, allow the eye to detect light intensities from the lowest to the highest observable without damage to any portion of the eye. This is seen when you're in a bright room and the lights go out. Your eyes will dilate, allowing more light into them. Thankfully, this is an involuntary muscle movement and automatically occurs with a change of light. In order to process the image and visual nerve impulses, images that hit the retina are passed into the brain. The optic nerve is the part of the eye that conveys signals received by the eye to the brain. The eye forms images upside down, but the brain turns them right side up, allowing us to see objects as they really are. A few interesting facts are that since light rays from a nearby object can spread out but still enter the eye, the lens must be more powerful or converging for close vision compared to distant vision. This function helps control eye relaxation and strength. For example, the eye is most relaxed when viewing distant objects. Vision of far objects is called totally relaxed, while accommodated is used for close vision, and fully accommodated is used for the closest vision. One of the most common vision deficiencies is nearsightedness, or myopia, which is having difficulty seeing distant objects while close objects appear clear. Myopia may be caused by either having a lens that is too strong or an eye that is too long. For example, reading is easy, but seeing billboards from the freeway would be difficult. The eye over-converges the parallel light rays from a distant object, and the light rays cross in front of the retina, making far objects blurry. In order to correct this, concave lenses are used, making the light rays diverge before entering the eye and reducing the power of the eye. For concave lenses, the focal length and power are negative, hence why those with nearsightedness will have glasses prescriptions such as negative 0.50D or negative 2D. Another common vision deficiency is farsightedness or hyperopia, which is difficulty seeing close objects clearly while distant objects appear clear. Hyperopia may be caused by either having a lens that is too weak or an eye that is too short. For example, billboards would be easy to see, but reading would be difficult. A far-sighted eye will not converge the light rays from a close object onto the retina. Instead, the rays will meet beyond the retina, making close objects blurry. In order to correct this, convex lenses are used, making the light rays converge before entering the eye and increasing the power of the eye. For convex lenses, the focal length and power are positive, hence why those with farsightedness will have glasses prescriptions such as positive 0.50D or positive 2D. One last common vision deficiency is astigmatism, which is an unevenness in the ability to focus the eye. Some rays passing through the eye will focus closer in comparison to other rays, resulting in an elongated image. Astigmatism is normally due to an abnormal cornea shape, abnormal lens shape, or unevenness in the retina. Due to these irregularities, the image will be produced in different locations, causing less distinct vision. Astigmatism may be corrected by wearing glasses that have the opposite irregularity of the eye. The eye is an amazing part of our body that we often take for granted. Through physical concepts, the eye allows us to see far, near, in darkness and brightness, and to see everything upright. Thanks to geometric optics, we are able to see all the beauty that surrounds us.